So it's my pleasure to introduce Igor Khavkine from the Czech Academy of Sciences, and he will tell us about geometry of analytic structures.
Thank you for the introduction and for the opportunity to talk here. I'm very excited for my first postdoc on so this is mostly a report on some work in progress. I will be waving my hands with me if I say something that's wrong. So I apologize for that. And also, I should acknowledge some help from Francesco, who helped me understand some things about G structures. But I say something wrong about that, you should assume that's my fault. Okay, so bar is staying there, but that's fine. All right, so I want to start with a canonical example of complex structure as a G structure. Right? So what are the ingredients of I'm trying to understand a complex structure as a kind of additional geometric structure on top of a real kind of thing. Okay. By definition of complex structure, we have basically a special atlas on a real single manifold, local charts of maps from Cn into the manifold, and the transitions between these charts should be homomorphic functions. Okay? So once we have these charts, what we do is we say, okay, let's take Jacobians. Right? So this so we get now what are called frames. So what are frames? Frames are just basically bases for the tensor space, right? And we get them by basically fixing one point at a time, differentiating directions, and that's the difference. Okay. So the result are sections of the frame bundle. Okay, so frame bundle is just some power of the subset of the power of the tensor bundle, making sure that all the components of the all the tuples of vectors are non-degenerate. And these the Jacobians of these charts give us the holonomic sections of this bundle. Right? So these are not arbitrary sections of the frame bundle. They satisfy one condition in terms of vector fields. This is that the vector fields have to sometimes people invert the frame and then get a full frame with one points, and then the condition, homogeneity condition, and that is like the individual one points have to be okay. So we look at the images of these local holonomic sections of the frame bundle, and we end up with a subset of the frame bundle. Okay, it turns out to be a subset whose fibers are they look like the structure group of the transition functions. So the transition functions are homomorphic, and locally they just end up being elements of GLM as embedded in the general group of arbitrary transformations of frames. And the way it sits there determines the geometry of this complex structure. Okay? And by the way, this is an example of the first order G structure. The first order means that also the fact that we're talking about the Jacobians, which essentially are first derivatives, or the same as first jets, throwing away information about the zero part of the thing. Okay? And this number could be higher, and this would correspond to a higher order okay. So once we have this G structure, which is a principal GLMC bundle inside the bundle of our manifold, we can ask questions about it. Okay, so if we know that it comes from a real complex atlas, then we know that it is integrable. Okay, and there are different degrees of integrability. So the final degree is, you could say, strict integrability, but given if somebody hands you a principal G bundle, GLMC sitting inside the bundle here, does it have polynomial sections, polynomial sections? Okay, if it does, we say it's strict integrable. Next level is formal integrability. We try to condense this condition to something that can be checked locally pointwise by taking some derivatives of some parameterization of this G bundle, which could be done to by somebody else. Okay, so turns out that so in this particular case, there's a well-known way to describe formal integrability, which is of course implied by strict integrability, which is the definition of something called intrinsic torsion, which is defining some intrinsic way based on the structure of the complex structure, given as a subset of the framework. I will not go into the details. This is kind of the material, and I think people in the audience know this much better than I do. So I just bring it up here because I'll try to talk about the analogy for analytic. Okay, so the description in terms of this principal G bundle sitting inside the frame bundle can also be equivalently stated in terms of some existence of some geometric objects. So, for example, the way that this complex structure is embedded inside the frame bundle can be thought of as adapted to a particular endomorphism of the tangent bundle, which plays the role of consider the complex squares and the vanishing of the intrinsic torsion, which corresponds to formal integrability, can be encoded in the vanishing of so-called in-house tensor of that complex unit, which is also known as an almost complex. And there's a celebrated theorem, the Riemannian theorem, which also tells you that if you have formal integrability, so the vanishing of this main house tensor, or equivalently the vanishing of torsion, then that actually implies the existence of local polynomial frames, which are adapted to this complex structure, which implies strict integrability. Okay, so this is a very nice picture, and basically the questions that we'd like to ask are: is there how good of an analogy can we make with that in the case of an analytic structure? Okay. What is an analytic structure? It is well, so starting from the basic definition, again, it's an atlas of analytic real analytic charts on a smooth real manifold. All right, and so these are maps from Rn with real analytic transitions. Okay. So again, we can take the bodies of these maps, and we have sections of different bodies of the charts. We have sections of the frame bundles, of course, following sections. By the way, just in case I think I forgot to mention, holonomic. Right. So I said that it corresponds to those frames that come from recordings of charts. Yes. Okay. So we have these frames, we can again look at them pointwise. But now it's so if you just look at the frames themselves at first order, analytic chart can have any equal, right? So there's no mistake. Again, if you look at second order, analytic chart can have any order. So you cannot find any pointwise restrictions on the derivatives of the charts that will tell you that we are analytic. So what you need to do is you need to really go to infinite order. Right? So what we get is an infinite order G structure where we need to take so the complete full infinite jets of the charts. Forget about the zero order part, so just keep the derivative. And what we get are actually a subset of the higher order frame bundles, which is just the jets of the frame bundle. So here I'm taking infinite order jets of the frame bundle. And now finally they no longer coincide. So if I was taking infinite order here, infinite order there, these objects coincide, but here they do not coincide. Right? So we get a proper subset of the infinite order frame bundle, as before, we get a principal G bundle where G is now the group of analytic diffeomorphisms of R and Rn, X and 0. Okay, so we again can describe analytic structure as a G structure, although of infinite order, using this structure. Okay, so there. Yes. I think that doesn't make any difference here, because I think the difference between Roman codes and other descriptions really matter when you look at global features, so global structures, and I'm looking at just small inputs. Okay, so we do have this kind of geometric description of one analytic structure. Now, can we answer the following questions? So what are the right analogous descriptions of formal integrability? Or does it make sense? Strict integrability. Is there some notion of intrinsic torsion? And if we have formal integrability, will we be able to recover a strict integrability like this? And so, is there some analog of for the analysis? And also, another interesting question is there some geometric object that would replace an almost complex structure that would produce an adapted analytic structure to it? Okay. And as far as I know, not a lot of attention has been paid to these questions in literature, but I would be happy to know otherwise. So here are the attempts that maybe try to answer this. So the first observation is that there is in fact an answer to how to consider strict integrability. Okay, and I found out about it in some previous way. So in 2014, out of idle curiosity more than anything else, I posted a question to Matthew about basically asking this question: is there such a thing as an analog of Riemannian for real analytic structure? And this question said idle for fact there were some quite repeatable members of mathematical who said that, well, of course they can't do anything like this because is a condition for analysis, not in geometry. But somewhat to my surprise, 4 years later, there was an answer posted by Steve, who referred to some of his own work, basically, to my satisfaction, answered this question. So here's this answer. First, I need to say something about a rather old notion of analyticity, that's not relative to a coordinate system, but relative to a frame. So if you have a frame, effectively on manifold, you can say that some function is analytic with respect to that frame. So if you have frame x, then we say that the function is x analytic when all the frame derivatives, so you just use these methods to really differentiate the scalar function, grow not higher than a certain rate. And this is the kind of the normal rate you expect coordinate derivatives of an analytic function. Well, if the frame is a coordinate frame, this is exactly the same as analytic. But if the frame is not holonomic, so the commutator between the kernel and so on and zero, this would be something else. Well, a priori you don't know. Or if the practices themselves are not analytic in some obvious way. Okay. So, yes. It's just a constant, right? So it depends. So around every point, so opening point is that around every point, for every point there is an R, and that R is uniform in some possibly small neighborhood of that point. So basically, you know that the coefficients of Taylor series of functions cannot grow faster than geometry. And so this is the geometric rate, and the n factor of what accounts for the derivatives that differentiate powers of the variable. Okay. So here's a Steve's theorem, which appeared in Akademie. I think it's not actually he didn't publish it anywhere. It's just but it stays the following. So suppose that we have a frame, smooth frame on smooth manifold. We can extract from it smooth functions, the structure functions, which are just the coefficients of the u values. Okay? Now, these are smooth functions. You can ask the question whether they're x analytic with respect to them. It turns out if they are, then you can extract a sub-atlas of your smooth atlas, right, which will be an analytic atlas. So the transition function between those charts will be analytic, such that the frame that you started with is going to be analytic in most cases. And of course, there are many different ways to extract an analytic sub-atlas from a smooth one, but this is a unique one, which is adapted to the frame. And this is possible when this condition is satisfied. So let me refer to that as Steve's condition. Okay, so what can it tell us about the analytic structures? Well, the conclusion I draw from this is the following. So suppose that we have an analytic structure given, let me call it an almost analytic structure, given as a sub-bundle of the infinite of the frame bundle of manifold. And if we have, so this is now a PD. Okay, so maybe in geometric approach to PDEs, a PD is a sub-manifold of infinite bundle of whatever the fields are, and here are the fields are the frames, and we have this PD node. Okay. So suppose that I have a solution of this PD with some frame whose jet fits inside A. Now, this is not necessarily a holonomic frame in the sense that it doesn't come from a capability of the chart, right? So, but it's a solution of this Okay? But so if this frame satisfies Street's condition, then it can be corrected to a holonomic frame. So you can take, if you take a solution of this almost complex structure, and the almost complex structure satisfies Street's condition, then you can apply to the G action at some given point, where G is this local to get a corrected frame, which is still a solution, but is also holonomic. So this tells you that Street's condition is the condition on the almost analytic structure for it to be strictly. Okay, and I believe that this is a good analog for Riemannian condition on okay. But notice that I started with a requirement that I had to have a solution of this structure. But as you may know, having a solution to a PDE is not necessarily a given. So it's when it's presented in this way, the subset of and so you need to prove that there are some actual integral and it's not true. So out there you don't know whether solutions of this type exist or not. So you can check pointwise whether Street's condition is satisfied for the almost analytic structure, but to be able to integrate it, you still need to satisfy the property of existence of solution. So this is something that actually I managed to do. I couldn't find this anywhere. So this is possibly somewhat new. So let me refer to two conditions on the almost complex structure. So I will call formal integrability the fact that this, as a subset of J infinity of frames, it is integrable. Okay, so it is compatible with the Pauli connection on infinite J quantum. Just the Pauli connection is the one that distinguishes polynomic sections of the J quantum from non-polynomic. And let me refer to Street's condition as exposure. Okay? So together they will be like the analog of the dimension of the main house concept for complex structure. So this is these two together should be the right notion of formal integrability for an almost analytic structure. All right. So here's a theorem that we can prove. If our almost analytic structure is formal to free senses, then it does have solutions in this sense. So if it does have solutions, then you can go and apply Street's theorem to get Street. And this is so. I want to show you the proof. So how much time do I have? 10 minutes. Okay, so I think I have time for that. And it's not so complicated, but it's like the logic is not so complicated, but it involves some computations, which I will show you, which a little bit involved, and it also involves knowing a somewhat obscure theorem from analysis. And I'm curious whether this theorem is obscure to the audience. Okay, so the idea here is to leverage the fact that we have a connection on this infinite dimensional bundle of our baseline. And so this is the finite infinite part of the thing. So the fibers are here infinite dimensional, but they're not so big because they're modeled on this group of local analytic. And we know that there are not as many analytic functions as there are all smooth functions, right? Because of these growth bounds on the Taylor coefficients of. So what we would like to do is to rescue Frobenius' theorem for the Poisson connection on this bundle. Right? It's well known that Frobenius' theorem fails in infinite dimensions, but here the dimension is not so infinite that you can't do it. All right, so how do we do it? Well, let's take some non-holonomic section of almost and so this is known by infinity. So non-holonomic in the sense that it's not the jet prolongation of some frame. Right? So forget the prolongation frames. In the sense that so it's just not a jet prolongation of any particular frame. But at the lowest order, there's some frame encoded in this tower of jet components. You know that by X. And I can use this X to basically identify the frame bundle with basically a bunch of scalar functions. So I can always write any other frame as scalar linear combinations of this basic frame. Okay, so it means that if I can identify the infinite jet bundle of the frame bundle with a bunch of infinite jet bundles called scalar bundles, as many of them as the components. Right? So we now reduce jets of frames to jets of scale. And so let's consider a Poisson connection here, okay, via the Poisson connection on this scalar jet bundle. And this is the equation for transport with respect to the Poisson. Right? The true derivative of some particular component, jet component of n, is given by the formal component of order n plus 1 corresponding to the direction u. Right? That's what the transport equation is. Good. Okay. Now what we can do is we can use this x infinity, this non-holonomic section of our almost complex bundle, to change coordinates on the frames fiber-wise. Okay. Basically, if I had a holonomic frame, what I would like to do is basically rewrite this equation using instead of coordinate derivatives, frame derivatives, symmetry. Right? So there's some combinatorics that goes in here because the frame derivative is compensated with right? Brackets. But you can do this, right? So if you symmetrize, then you can basically rewrite this using some recursive formulas, and what you end up with is something like this. Right? So the true next frame derivative is equal to the formal frame derivative of one higher order plus lower order terms or terms of the same order as the differentiating or lower, with coefficients that depend on basically derivatives of the structure functions of the frame and their derivatives. And it takes some effort to complete this, but you can do it. So this is the new version of the Poisson transport equation. And this is the part that uses the one higher derivative, formal derivative, and this is the part that uses same order or lower. And you would expect that this part will be somehow unbounded, okay, and that will complicate your life, and maybe you would expect this part to be bounded on this space of jets of analytic type. And maybe this is my initial idea. Okay, so then we do something with the unbounded part, and this is we can maybe show resistance different times. So there are two surprises that I found in trying to investigate this. So first is that actually both of parts end up being unbounded. So this part is unbounded for obvious reasons because you can use regularity with the high probabilities. And this part is unbounded because it just has one. But if you assume Street's condition on this that it holds local and holds particular for this non-harmonic section of the almost analytic structure, then these are not too unbounded. Right? So this, both this operator and that one, they they satisfy a bound of this type. I have to explain it a little bit. So what I'm doing is, I forgot to put the subscript here. So there's a whole bunch of analytic norms, which each one for different reads of convergence. You can ask, I have some Taylor series, does it converge on this radius or this radius? And if it converges on a larger radius, there's a stronger norm than one converges on a smaller radius, and some relations between them. So you can index these norms by the radius of convergence. And these operators turn out to be bounded if you go from jets that have large radius of convergence to small radius of convergence. And of course, the closer the two radii converge to each other, the larger the norm, because it's unbounded for exactly the same radius. So this is reflected by having this denominator, which registers the difference between the radii of convergence of the. Okay? And so there was one surprise that that part was unbounded in the same way as the first part. Okay? And the second surprise is that there's a kind of packaged theorem in the literature that we use to integrate this kind of thing. Okay? So basically, everybody knows that we use the Par's theorem for resistance of solutions of these on Born spaces. Okay? When we have an equation of this form, and this right-hand side is bounded. But it turns out that you can do the same when you have a scale of Born spaces. Okay, so some of those spaces are one example, but these spaces are analytic jets or Taylor series with different versions. And when this operator on the right hand side is bounded, but also is allowed to become unbounded as the indices of the scales come closer to each other. So this is called Ovsyannikov's theorem, which was proven in 1965, and independently by Trev, but he quickly realized that it was proven by somebody else, and so he also refers to it as Ovsyannikov's theorem. So it basically tells you that when these bounds are satisfied, which is almost exactly the same as the option later, then this transport equation has a solution which exists at least for some short time, and you can bound the weaker norms of the default solution by the initial strong norm. And if you interest parameters, this the dependence on parameters also preserves regularity. And this is how you can convert this ODE existence theorem into Frobenius theorem for this kind of transport equation. Yes. Okay. So I'm glad that I could get this out of the way because basically what I can say next is that well, we don't know. That is, I don't know how to get the analog of the almost analytic homomorphism or the main house tensor conditions as a geometric way to describe almost analytic structure. I suspect that this should have something to do with elliptic equations. So maybe special elliptic equation for some condition would actually give you an adaptive analytic structure. But there are some basic counterexamples that tell you that at least this condition should be non-empty, but I don't know at the moment what that's. Okay, so with that I will do. So just trying to explain to you that analytic structure can be thought of geometrically. In course of doing that, you need to rely on the interesting interplay of some new and classic results from analysis and geometry. And there's some interesting open questions that should be studied and something about. And of course, if you can find some something that exists in literature that you think is relevant for this, I'll be very happy to hear it. Or if you can think of more examples of model examples, that's great. So thank you for your attention.
Are there any questions? Okay, yeah. So if there are any other questions that anyone else can discuss about?
Yeah, I have a question. So real analytic functions are dense in the space of smooth functions in this very fine Finite-infinite topology. Does your approach give another proof of this? Because the proof of this always goes back to a theorem of Grauert, where I always had difficulties understanding all the details.
You mean this proof goes the embedding in a Stein complex too? Okay, so the answer is I don't know. So I really haven't thought about it.
Okay, thank you.
Okay, any other questions online? Okay, I think then we should thank the speaker again.